Okay, hey everyone, Mr. Fusco here. I'd like to do number 13 with you. It was part of your last problem set. Obviously, the due date for that has been postponed indefinitely. Um, anyway, let's get started on this. So you start walking from the origin in the direction of a vector 3, 1 with the intention of ending at point 7, 1. You're allowed to make one right-angled turn. Let's just focus on part A for now. Find Part A, the point at which you make this turn. Okay, let's just start there. So the first thing I want to do is make an accurate diagram of the picture. So I'm going to start with a coordinate plane, and it says that I start at the origin. So that vector 3, 1, we walk it in that direction. So 3 units over 1, 2, 3, just approximately, and 1 unit up. So that's my vector 3, 1. That's my vector 3, 1. And I walk along that direction. And if I keep walking along that direction, of course, I would eventually go out infinitely in that direction. But I want to get to point 7, 1, right? I want to get to point 7, 1, which would be 1, 2, 3, 4, 5, 6, 7, 1, which would be about right there. That would be point 7, 1, right? Okay, now obviously, if I just walk in the direction of vector 3, 1, I'll never get there. I'll just keep on going out into space, right? But at some point, if I make a right angle turn, I can get there. And it's, it's obvious if you look at the diagram, it should be somewhere around here. But the question is, exactly at what point is that? And we don't know. All right, we don't know what point that is exactly. Now, the way I'm going to tackle this problem is by first saying, well, if everything is based off of the origin, I can make a vector at 0.71. I'm going to turn that into a vector stretching from the origin. So that 0.71 is now effectively a vector. So now it's 7, 1 as a vector. Okay? And the concept we're going to use here is the concept of a projection. What we want to know is how to get to here. At what point do we make that turn? And I can symbolize that by that blue vector that I've just drawn in there. Now the question is, how do I find that blue vector given the information? We have two other vectors. So if we want to take these two vectors and get a third, okay, now you might think, oh, a cross product, two vectors to get a third, but the thing is, all three of these vectors are in the same plane. And remember, the cross product will give you a vector in another plane. So we're not going to use the cross product. What we are going to use is the projection of one vector. We'll call it vector A onto another vector, vector B. And if you remember, that's the dot product of vector A and B all over the dot product of vector B times vector B. And basically, you can remember it, vector A projecting onto B, A dot B, and everything else in here is the vector you're projecting onto. That is the vector you're projecting. Okay, so I'd like for us to get some intuition for what a projection really is. So basically what we're doing is we're taking one vector and we're projecting it onto the line that another vector is basically existing on, right? So that vector 3, 1 exists on this line here that I've drawn that extends out in both directions infinitely. So here's a visualization we can use to see what's going on here. All right. So first of all, let me name these vectors. So this is going to be vector A, and this is the vector I'm projecting it on, vector B, and we'll call the newly projected one vector C. Okay. All right. So in other words, we could say that this projection is equal to the vector C. All right. Okay. So let's get that visualization going on. So essentially, you could imagine that whenever you're doing a projection, A onto B, that you're shining a light exactly perpendicular to the line that vector B is on. So there's, and we keep shining down. Okay. But vector A gets in the way, and the light can't go through. Oh, And now we can go through again. So essentially, the shadow of 7, 1 onto the line that 3, 1 is on, that vector that fills that shadow there is equal to the projection of A onto B. Okay, so if we can calculate this vector, then we'll know also the point at which we'd have to make that right angle turn, because we're starting everything from the origin, so that vector is going to be equal to the point at which I make that right angle turn. Okay, so now let's get down to business and actually calculate what this vector is. We know that the projection of A onto B, the dot product of A dot B, so A is going to be 7, 1 dot 3, 1 all over 3, 1 dot 3, 1 all times B, which is 3, 1. Okay, so there you go. Now all we have to do is calculate this. Okay, to calculate the dot product, fairly straightforward. You multiply like terms. So 7 is the x component of vector A, and 3 is the x component of vector B. So we do 7 times 3 is 21, plus 1 times 1, which is 1, all over 3 times 3, which is 9, plus 1 times 1, which is 1. So you get 22 tenths. So the projection of A onto B is equal to 22 tenths times the original vector, which is 3, 1. Okay, we could simplify that even further. We can multiply that 22 tenths on through there, which would get us 6.6, 2.2. That vector C there is equal to 6.6, 2.2. So the point is going to be parentheses 6.6, 2.2. So it's the same as the vector, because remember, if the vector starts at the origin, then the point is equal to the vector there. Okay? All right. So we know that we're going to make that right angle turn at point 6.6, 2.2. And so that is the answer for part A. Okay, so for part B, it says, how far did you walk in the 3, 1 direction? Well, the distance we walked will be equal to the length of my projected vector, that blue vector right there. And how do you find the length of a vector? Is equal to its magnitude. Okay, so all we have to do for part B is to find the magnitude of C, which should be no problem. We know that in general, to find the magnitude of any vector, cx squared plus cy squared square root equals the magnitude. And that's essentially just Pythagorean theorem. Okay. 6.6 squared plus 2.2 squared square root equals the magnitude, 6.96 units. Okay, that is part B. Okay, for part C, I wanted to start with a clean slate because it was getting a little bit cluttered. So, all right, for part C, the question is how far you walked orthogonal to the 3, 1 direction. All right, so let's just redraw this diagram real quick. Okay, so we have our projected vector, vector C right there, the blue vector from the last part. And what it's asking for us now is how far you walked orthogonal to the 3, 1 direction, which we know the 3, 1 direction is along this line, so the blue vector is in the 3, 1 direction. Orthogonal is just basically a fancy word that means make a right angle. Okay, so perpendicular, orthogonal, normal, all those things mean right angle. So basically we want to know how long this piece of the triangle is right here. So I'm going to actually do that in a different color. Why not red? Okay, so we want to know what the length of this piece is here. Now, basically, what I want you to recognize here is if I'm asking you to find this piece, remember that when we add vectors up, we add them up tip to tail. So we have, that's my blue vector, plus the red vector will give me the resultant, which is my black vector right there. So I can express that as, well, let's just rename these. So we'll call, I'm renaming this vector A, vector B, and vector C. So I just renamed them all there. So I can write that as A plus B equals C. Remember, vector A is 6.6, comma 2.2 plus, and we don't know vector B, so I'm going to fill that in with bx, which is unknown, by, which is unknown, and vector C, which is known, is 7, comma 1. So this is our vector sum right here. Basically what this is basically two equations in one. Basically we have 6.6 plus the next x component, which is bx, equals 7. Okay? And then for the y components, we have 2.2 plus the y component of b, which is unknown, equals 1. Now, hopefully you can see we could figure out the components of bx and by very, very simply. So bx is equal to 7 minus 6.6. by is equal to 1 minus 2.2. So we get that bx and by are 0.4 units and negative 1.2 units, okay? And that should make some sense. We know that this thing is moving over to the right, so we're going to have a positive value, but it is going down, so that negative 1.2 represents the fact that it is going downwards. So that makes perfect sense. It's a reasonable result there. Okay, but that's not the question. It says how far you walked. Okay, so that tells me that my new vector, which is b, which is equal to 0.4, negative 1.2. I want to find the length of that vector, which we know is the magnitude. Okay, 0.4 squared plus 1.2 squared, and again, because we're squaring it, I'm not even going to worry about the negative sign there. Square root to find the magnitude. 1.26 units. And that is the answer for part C. I certainly hope you found that helpful. Thank you so much for watching.